Welcome to the calculus class on this March 27th of 2017. Today, we are going to get into some mind-blowing stuff. But before we do that, I want to look at this example one more time. Stir my screen so it doesn't shut off. This is a left Riemann-Sum, left rectangle method. And right now it's 5 rectangles. I've set the number of rectangles at 5. And we have a pretty accurate sum. Owen came up with this function, by the way. Shout out to Owen Sonnenberg. Based on those 5 rectangles, the current sum it's calculating for us is 116.6. And we can see it's missing some gaps underneath, well, it's estimating the area of the curve. So in sum notation, the basic way we do this is whatever the base of the rectangle is times the height. So I'm going to do it backwards. That's what we're doing. We're adding up rectangles. Each rectangle is base times height. I know this isn't the way we usually write it, but and we start at, let's say, 1, and we go up to 5. In other words, we're adding up rectangle 1, 2, 3, 4, and 5. So I've never written it exactly this way, but do you see that this represents the area that has been calculated for us? It's the area of a bunch of rectangles. I use the little subscript I to represent rectangle 1, rectangle 2, rectangle height 3, rectangle height 4, and rectangle height 5. Now what happens if I increase this to, say, 10? What happens?
Go on for the list till the number 10 on the number line.
Oh, I'm keeping the same interval. I'm not going to change the interval.
Move the 5 so it's exactly 5.
And I'm not worried about the conversion. I'm just saying a bunch of heights and bases.
Are you saying you want 10 rectangles?
Yeah, what happens if I make 10 rectangles?
Okay, you have to put 10 on the top. And then on the bottom of that, on the equation, you have to do 1/2.
Yeah. So if we were actually doing this and typing it into our calculator, I'd have to do a lot of adjustments. But this, I purposely use like a generic notation that kind of covers it. This is 10 rectangles for the same thing. And it gives me a different answer. Slightly bigger answer. I can see there's less gaps that it's a more accurate answer. I think you can answer this question. What if I plugged in 80 rectangles?
8 times more accurate.
This goes out to 80. And you can see it like very closely approximates that area under the curve. I have a very accurate answer, 124. I can tell visually it's pretty accurate. Is it exact?
No.
No. So the question is, what number can I plug in to get it exact?
Infinity is not a number, it's a size.
And that's great if infinity was a number, that's exactly what I would plug in, right? But I can't plug in infinity. But I want to look at what happens as it gets closer and closer and closer and closer to infinity. And you have in your pockets, probably you forgot about it because it's been in your pockets since the fall, a mathematical tool that helps you describe what happens as things get bigger and bigger and bigger. I want this to be infinity, but I can't plug in infinity because then it's just a bunch of errors. Yes. What Brian said, for those who didn't hear, was we can't plug in infinity, but what we can do is take the limit as we approach infinity. So what we have here, and this is going to come up in our notes in a second, but what we have here is an expression that represents the exact area. Because that's what a limit is. It looks the value that it's approaching and it says, okay, that's the exact. So if we take an infinite number of rectangles, essentially, we get this. So instead of typing this in each time, we have a new notation. called integral notation. And I think at this point I'm going to shut the screen off and get right into the notes. So the title of these notes, I think we'll get into by the end of class. Fundamental Theorem of Calculus. Probably the most important theorem in all of calculus. But we're not going to get into that right away. We first need to talk about some notation. Okay? So, because this is a very messy looking equation, it's got a limit, it's got a sigma, it's got a bunch of stuff in it. I just need a cleaner way to be able to write this. And so, we have a new, I should have looked up what letter this is. I always forget what letter it is because it's just known as the integral symbol. That's it. Can you guess how this matches up with this stuff? Like what that says?
Well, would B be N?
No.
A B N.
A and B are actually not in here at all. A and B are the 0 and 5 that were on our picture.
So A is 1, B is N.
So what it means is
The f of x of b is like the top part of the derivative. So I assume it's like the limit part of it. Did I say? To assume?
I think I was asking a bad question. What it means is it's the area under the curve. Which curve? F of x. That's what the function is. F of x. From A to B. In order to take the area under curve, I need to specify which parts of the curve I'm looking at. That's all it means. If you want to draw a picture, I encourage that. Here's a random curve. There's A, there's B. And the integral, so that's f of x, is the area from A to B, which you can symbolize by shading it. Does anybody want to take a stab at actually reading how I would say that, those symbols?
The integral.
That's correct. When I see that symbol, the first thing I should think is integral. The integral of. Actually, I'm going to really erase the word of.
The integral A to B.
From A to B
Of f of x
of f of x
d of x.
dx, or d. One thing I'm not going to talk a lot about today is that little dx. It's not super important. Right now, all I want you to understand about it is that little dx there, that's telling us what the variable is. Kind of like how we had dy dx before, and then we're taking the derivative of y with respect to x. This means we're integrating with respect to x. So, alright. Definition. I know it just seems like I did two definitions. I already told you what it means in a picture and how to read it. What else do you need to know? The mathematical definition. And I've already done it for you. The integral from a to b of f of x defined as, do I want to change my notation at all?
I don't know.
That. The limit as n goes to infinity of each base times each height. Yes, and we'll leave it like that. With the understanding that there's not really a direct correlation between like f of x. I know I get the height by plugging it in, but
What's the thing? What's the bottom part under the e? The e there?
I equals 1.
I equals 1?
Yeah. So we're going from rectangle 1 to rectangle n.
And that's h times v.
And this is h sub I, meaning the height at a certain interval
Oh, times b.
times whatever the base is, which would be a constant.
Alright.
And then the limit part means we're taking an infinite amount of that.
Yeah.
Essentially. Alright. So, we have not gotten to the fundamental theorem of calculus yet, but let's do an example just to see if we, let's do 2 examples. Just to see if we understand this notation. Example 1. The integral from 0 to 10 of, what's the most basic function you can think of?
F of x. Y equals x.
Yeah, f of x equals what?
X.
That's, I'm gonna go even more basic than that.
1.
1. Any kind of constant. I'll do just for fun, I'll do 5. And the other thing I need to say is what's the variable? I'm gonna say x is our variable.
Is that 0 to 10?
From 0 to 10 of 5 dx. How do you interpret that? I haven't taught you how to do these yet, by the way, but I'm picking special examples that you do know how to do based on what the shape looks like.
That's just gonna be 50.
It's just gonna be 50. How do you know that?
Because 5 times 10 is 50. It's just perfect rectangle.
It's a perfect rectangle. So what this question is asking, and you can picture this in your head, and that's fine. Your homework is going to be problems like this, by the way. It's a rectangle that goes from 0 to 10, and it stays at 5. So the area equals 5 times 10, which indeed is 50. The integral from 0 to 10 of 5 dx is 50. Good work. And I don't want you to forget, once we start doing more complicated things with these, that you still have this available to you. If it's a simple equation, you can sometimes just picture it and get the answer. Let's do one slightly more complicated one, and then we'll get into the fun part, the fundamental theorem. Let's go from 2 to 5, and let's do a linear but not a constant function.
Lisa, how do you write the answer?
50.
It would just be a equals 50.
Yeah, if I were to, I could write it here if I want to, equals 50.
Okay.
And there's my thought process. This one's a little trickier. I could have gone straight for a triangle, which you would also be able to do easily, but instead I went for a different shape.
Okay.
Can you picture what that'll look like?
Yeah.
3x is a straight line that goes up, but I'm going from 2 to 5.
Quadrilateral.
It's a quadrilateral, but not an easy quadrilateral to find the area of.
It's a hexagon, super easy.
It's not a hexagon. It's only got 4 sides.
I think you
No,
meant
it's,
it.
I'm sorry, it's a trapezoid.
There we go. It's a trapezoid.
Everyone knows the trapezoid formula, as Mr. Ori would say.
And as I said last time we were together, everyone knows the trapezoid formula. This happens to be, I don't know how many people would look at that and see a trapezoid immediately.
I would, yeah. I
But that's a trapezoid because it has parallel sides. It has parallel sides because we're taking the area under a curve from 2 points straight up. The way I remember trapezoid is it's just the average of the 2 heights, but the formula, in case you forgot, is
If it's the average of the 2 heights, I'd say it'd be height 1 plus height 2.
height 1 plus height 2, b1 plus b
times
divided by 2 times the
times
actual height.
yeah.
So this is the formula, but take note that our trapezoid is on its side.
Oh, that's hard to remember then.
So there's our, it doesn't matter what's b1 and b2, but I'm just going to do b1 and b2 like that. And there's our h.
Okay, but like how do we do it with this other thing?
Alright, so what's b1 and b2?
It's 2 and 5.
Nope.
6 and
The height.
6 and 15.
where are we getting those numbers?
Where'd you get the 6?
You plug it into the function. You plug 2 into the function. 2 times 3 is 6.
Function.
What?
3x.
The function where
Oh, I see what you did. Alright.
So to get the height, it's the same as plugging into the function. Good point. And whatever that is, times the actual height, which is actually more like our base in this one. 5 minus 2, which is 3. And I don't feel like doing that. Everybody do that already for us? 21.
Oh, dang it. 1 times 3.
21 divided by 2 times 3.
That'd be
10.5.
10.5 times
31.5.
31, yeah.
Perfect. How are we doing on time? 43. Alright. I think I am going to stop there today. I know. So, I made a big promise at the beginning of this, and I failed to deliver. I said I was going to blow your mind, but really all I did today was introduce a new notation. Tomorrow, I promise I will blow your mind with a fundamental theorem of calculus. Tonight's homework is going to be several examples like that. We're going to spend the last 10 minutes of class practicing.